Good day everyone. So today I will explain about the technical problem in our project. This project focus on designing a 24-volt DC shunt motor that satisfies the required operating specification. The main objective is to achieve a rate speed of 1500 rpm while maintaining a target efficiency of 80%. During the design process, one of the main challenges is minimizing electrical and mechanical losses, including the armature couple losses, field couple losses, and rotational losses, as these losses reduce the overall motor efficiency. Besides that, important performance parameters such as back EMF, armature current, and the torque speed characteristic are analyzed to understand the behavior of the motor under operating condition. Finally, the motor design is verified through analytic calculation and simulation to ensure that it meets the required specification and operate efficiency. So next, I will explain about the project principle. This project is based on the operating principle of DC shunt motor, where the field winding is connected in parallel with the armature winding. When a 24-volt DC supply is applied, current flow through both the field and armature winding is creating a magnetic field required for the motor operation. The interaction between the magnetic field and the armature current produces electromagnetic torque, which causes the motor shaft to rotate. During operation, a back EMF is generated to oppose the applied voltage and regulate the armature current, and helping the motor maintain stable performance. So finally, the motor performance is evaluated using analytic calculation, mathematical modeling, and simulation, where parameters such as current, torque, speed, power flow, and efficiency are analyzed and compared with the simulation result.
Okay, my name is Arati Shakiraniami, and I'll continue talking about the design and the specifications of the DC shunt motor that we have designed for the simulation, as well as the mathematical analysis in terms of the formulas that will be used to determine the various types of variables for the report. So for the design planning, the machine type is DC shunt motor. The rated terminal voltage is 24 volts, line current 6 amperes, power rating 144 watts. The shunt field resistance as well as the armature resistance is 120 ohms and 0.5 ohms respectively. Rated speed 1500 rpm. They have 2 poles. The flux is 0.002 webers, and the goal design efficiency is 80%. The core material is laminated silicon steel core, and the winding type is copper lap windings. In terms of the analytical circuit analysis, the first thing that we need to find and calculate is the field currents as well as the armature currents. For the field current, we simply used Ohm's law, which is V equals I times R. But because we are here trying to find the field current, we swap out the variables and we find for IF, which is equal to VT per RF, and that equals to 0.2 amperes. For the armature current, we use Kirchhoff's current law, where IA, the armature current, is equal to line current minus field current, and that would equal to 5.8 amperes. In terms of the back EMF analysis, we use Kirchhoff's voltage law. The original formula is VT equals to EA plus IA times RA, but because here we are looking for the back EMF, we simply switch out the variables where we find EA, and it would equal to 21.1 volts. For the machine constant flux, we use the formula that can be seen on the screen, EA over omega m. The value for omega m is the rated speed, which is still in RPM, that will be converted into rad per second, and 1500 RPM is equal to 157.0.8 rad per second. And we just divide EA by the value of omega m, and that would conclude 0.1343. For the machine constant, we just divide the value with flux, and that would equal to 53.72. The total conductors, Z equals to K times 2 pi, is actually derived from the K formula, where K equals to P times Z divided by 2 pi times A. But here, because we are assuming that P equals to A, those values would be crossed out, and that would leave us with K equals to Z over 2 pi. So if we rearrange the values, we would get Z equals to K times 2 pi. And that would if we enter the values of K and 2 pi, we'd get 337.5, but because there aren't any decimals for conductors, I rounded it up to 338. For the winding turns, we just simply divide the total conductors by 2 and we get 169. For the next calculation is the torque speed characterization. And first, before we get the speed, we calculate for the induced torque, which is 0.779 Newton meters. For the torque speed, we use the formula that can be seen on screen, and inserting all of the values that we have found before, we'd get 157.122 rad per second. For the efficiency modeling, the formula that we will be used is N equals to P out over P in times 100%. And before we put those values into that final formula, we have to figure out what the input power as well as the output power is. So for the total input power, we simply use P equals to V times I, and inserting all the values, we get 144 watts. Next, we calculate for all of the losses, and the first loss is the armature copper loss, which is 16.82 watts. Field copper loss 4.8 watts. Required output power 115.2 watts. So for the required output power, is simply just calculating the required output that isn't using the loss calculation. So this is just the required output that will be needed. But afterwards, we're gonna also calculate for the actual output power. So for the actual output power, we also have to calculate the converted mechanical power, which is 122.338 watts, and the rotational and core losses, which is 7.18 watts. So for the actual output power, we use the formula P out equals to P converted mechanical power minus P rotational, and we get 115.2 watts. So the actual output power as well as the required output power according to the calculation that we have made in this area is the same. So for the motor efficiency, we just insert the values. P out is 115.2 watts divided by P in, or 115 watts, and we get 80%, which is in accordance to the design that we aim to create at the start.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Alif. So in chapter 3, we validated our decision motor design using MATLAB simulation to verify our analytical calculation. So here's our simulating model. We have 24 DC source connected in shunt configuration, armature and field windings in parallel DC machine block with our calculated parameters RA 0.5 ohm and RF 120 ohm. So the load torque here is 0.733 Nm applied through the TL port. So it acts as a constant block. So here is the scopes to monitor speed, current and torque. So we set the simulation time, stop time 5 seconds, and with the solver we choose ODE 45 dormant prints. Let's run this simulation. Okay, so when I open the armature current, so as we know, we have starting current between 50 and 45 ampere because no back EMF at 0 speed, and then it settles down to 5.8 amperes after 1.5 seconds, exactly matching our calculation. So for the speed response, it starts from 0 and reaches 157 specifically rad per second or 1500 rpm, our rated speed. So it shows excellent agreement for the field current. Field current stays on the 0.2 ampere, and the armature current is correct to 5.8 amperes and only 0.03% error. Last one is increase armature resistance. So we want to increase RA from 0.5 ohm to 1.0 ohm to simulate heating effect. Alright, so let's see the result after we run this. Okay, so as you can see here, the speed dropped to 1294 rpm or rad due to higher voltage drop. This shows resistance significantly affects the speed regulation. On to the test 2. So test 2 is field weakening. So we increase the RF from 120 to 150, reducing the flux by 20%. So let's run it first. We'll see about the speed in rad per second. So voila, as you can see, the speed is increased to between 140 rad per second until 160 rad per second. So above rated speed, but armature current increased from 6.82 ampere to maintain the torque. Here it is. So this demonstrates the field weakening technique used in industry for speed control above base speed. So this simulation successfully validates our design. It meets all specifications. This leads us to our discussion and conclusion in chapter 4. So before I end, this is the power flow. Input power 144 watt, field copper loss 4.8 watt, into armature copper loss 16.82 watt, into rotational loss 7.18 watt, and lastly output power 115.2 watts. So the efficiency here, it becomes 80%, but there also loss over here.
I will present about the discussion. So basically the discussion is more about the design DC motor. It successfully meets the required specification of 24 volt, 6 ampere and 1.500 rpm, and lastly the efficiency is 80%. The field current of 0.2 ampere provide a nearly constant magnetic flux for stable speed operation. The armature current of 4.8 ampere allows most of the input power to be converted into a useful torque. The back EMF of 21.1 volt is close to supply voltage, indicating efficient motor performance. The motor developed an electromagnetic torque of 0.779 Newton meter, which is sufficient of required load. The motor operates at the rate speed of 500 rpm is equal to 157.12 radian per second while delivering the required output power. The calculated result confirm that motor design is efficient, reliable, and suitable for small-scale DC motor application. So lastly, for the conclusion slide, motor design consider all major power losses and still achieve the target efficiency of 80%. However, the analysis confirmed that the design calculation were accurate and that the motor operated stably. So the overall is the proposed decision motor met all project requirement and is suitable for a small-scale industrial and educational application. So in the future, the design can be improved through simulation study and optimization and prototype development.